Section 9.2, ellipses. We are going to look at the second of four conics. An ellipse is a set of all points x, y in a plane, the sum of whose distance from two distinct fixed points called the foci is constant. So what that means is if I can take any line going from one focus, hit the ellipse on the outside and then back to the other focus, that distance is the same no matter what. So even if I go over here and then back here, distance is the same. If I go up here, there, the distance is the same. If I go all the way across through the focus to the outside and then back to the focus, that distance is the same. So that's by definition what an ellipse is. Now let's talk about the horizontal and vertical. So you can see the horizontal ellipse is stretched more horizontally and the vertical is stretched more vertically. Once again, to kind of zoom in on these are the important points that we will be discussing. You have your center, and then your major vertex going horizontally. You can see that distance is the farthest away from the center, and then you have your minor vertices going perpendicular to your major. And then you have your the focus or the foci on each side of the center as well, in between the major vertices though. For a vertical, it's the same thing, it just goes the other way. So once again, you can see the center, but now your major is up and down, that's the vertical part, and then your minor goes perpendicular to that. So let's take a look at the equations of each of these. So the equation x minus h squared divided by a squared plus y minus k squared divided by b squared is equal to 1, and that's for a horizontal ellipse. For the vertical, it's the same thing, except you'll notice that the a squared and the b squared are switched. Well, what is that? Well, a is the largest number in the denominator. So if the a squared is the largest, and it's underneath the x squared, think x-axis, and that's horizontal. If your largest number is underneath the y squared, then you can think y-axis, and that would represent your vertical ellipse. Now let's see what we're talking about in terms of the hk and the a squared and the b squared. I'm going to zoom into the horizontal one again, and I'm going to label a couple of things. So from the center to the major vertice, that has a distance of a. From the center to the minor vertice, that's a distance of b, and then from the center to the focus, that's a distance of c. So those are the distance that we're discussing, and then the center, just as a circle was, that has a value of hk. And so your a squared, you can see, or your a is always your largest distance from the center to the major vertex. And so in your equation between the a and the b value, a would always be the larger in the equation. And once again, if a is larger underneath the x, it's horizontal. If the a squared is larger underneath the y, it is vertical. So I've shown you what a, b, c, and hk represent. On the next slide, I'm just going to kind of put it into words, but you have everything kind of as a picture as well. The major axis contains the center and the foci, and obviously it also contains the major vertices. The minor axis is perpendicular to the major. It contains the center and, once again, the minor vertices. HK is your center. C is the distance from the center to the foci on both sides. B is the distance from the center to the minor vertices. And then 2B would be the length of the minor axis. So in some problems later on, it's going to tell you that the length of the minor axis is 10. Well, that means that B value would be 5. Same thing for A, distance from the center to the major vertice, 2A being the length of the major axis. And as a reminder, that's the largest number in your denominator. And then there's a relationship of A, B, and C that I'm going to discuss as well. And I can clarify this in class if you have any questions. So we know that the distance from the center to the foci is C units. We know the distance from the center to the minor is B units. Okay? So if I create this triangle, you can see that this distance would be b squared plus c squared. It would be equal to this. Therefore, that represents the square root of b squared plus c squared. Same thing on the other side. That would be the square root of b squared plus c squared. Now, this gets back to the definition. The distance from this foci to the outside of the ellipse back to this foci, or focus, is constant. And so what does that represent? Well, if you think about what I was talking about earlier, if I go all the way across here and then back, what would that distance be? From one focus all the way across, so that would be C, C, and then that entire distance there would represent A, but then you're going back, okay? So that would represent that entire distance would be 2A. So all the way across and back would be 2A, which means every time that I go to the outside and back would be 2A. So 2A is that constant, and if it's equal to B squared plus C squared plus, or the square root of it, so there'd be two of them, and if we divide by 2, A would be equal to the square root of B squared plus C squared, square both sides, and you get A squared is equal to B squared plus C squared. So there's a relationship between A, B, and C. We're going to write this as C squared is equal to A squared minus B squared, because in most cases, because we have the equation with A and B in it and we don't have C, we're just rewriting it so that we can find the C value. But we all know that A is that largest length there, so C squared is equal to A squared minus B squared is that relationship. Alright, there's going to be three types of problems that we look at really with all the conics. 1, can we graph it? 2, can we write the equation? And then 3, can we work backwards? So those are the three problems we're going to look at. We're going to start with the graph. So I'm going to give you the equation in the correct form. We're going to identify the important parts, and then we're going to go ahead and graph it as well. So what do we know about this? Well, because the A squared is the largest, and it's underneath the X value, we think X axis. So therefore we know this is horizontal. We know B squared is 4. C squared, that relationship, C squared is equal to A squared minus B squared. So 9 minus 4 is 5. And then to get the actual distances, we take the square root of each of these. And the square root of 5 is approximately 2 point something, and that'll just help us kind of count to graph. The center is located at -3, 1. So that goes to your H value. Remember, it's X minus, so it's X minus a -3. That's what makes it positive. And then Y minus K, which would be a positive 1 there. And so your center's at -3, 1. The foci is the distance C, the major is the distance A, and the minor is the distance B. Now because this is horizontal, all those main points are going left and right, which affect the X value. So the foci, which is approximately 2 point something, but we want to do the exact value, we're going to take the X coordinate and add and subtract the square root of 5. So -3 minus the square root of 5, 1. And then we'll do -3 plus the square root of 5, 1. And all we're doing is adding that square root of 5 to the X coordinate because we're going left and right. So the center is at -3, 1. So we're going to count 2 something to both sides. So here's the center, 2 point something somewhere around here, 2 point something somewhere around there. So those are your foci. The major is 3 units. So we'll go 3 units to the left and 3 units to the right. All I'm doing is adding 3 and subtracting 3 from the X coordinate to find the points. But I'm going to count over here. 1, 2, 3 to the right. That's the 0, 1. And 1, 2, 3 to the left. And that's the point -6, 1. Minor goes the other way. So now we're going to take the B value, which is 2, and add and subtract 2 from the Y coordinate. So if I take 1 minus 2, that's -1. If I take 1 plus 2, that's 3. So over here on the graph, I'll just count up 2 units. 1, 2, that's at -3, 3. Down 2, that's at -3, -1. And then you can just graph the best ellipse that you can through the major vertices and the minor vertices. And that's it. So given the equation, find the important pieces, and then make sure you graph. And once again, with the foci, I want the exact point when you're using the square root of 5 here, but when you're graphing it, you're just going to count 2 point something to both sides. Alright, the next part is to write the equation in the correct form. So you got 4x squared minus 8x plus y squared plus 6y minus 3 is equal to 0. Now on this, similar to a circle, but you have a coefficient in front, and you can't divide by that because then you create a 1/4 here, which now you can't complete the square there. So where a circle you can do that because the coefficients would be the same. With an ellipse you can't. You need to factor out the ellipse, factor out the 4. So that would be 4 times the quantity x squared minus 2x plus blank, because we're going to complete the square. The y squared didn't have a coefficient, so I'm just going to rewrite that as is. And then we'll add the 3 to the other side. And now we need to complete the square. So half of negative 2 is negative 1. Negative 1 squared is 1. Now here's the part that we don't want to mess up on. Even though we added 1 to complete the square, it was 4x squared minus 8x plus 4. So we actually need to add a 4 to the other side, not a 1. And then on the other one, half of 6 is 3. 3 squared is 9. And then if you add that, you get 16. And we need this to equal 1, so we're going to divide everything by 16 to get our equation. And our equation would be x minus 1 squared divided by 4 plus y plus 3 squared divided by 16 is equal to 1. So that's how you write the equation. On this one, I'll go ahead and graph again just so you can see a second example of graphing an ellipse. So what do we know? We know a squared is 16, b squared is 4, c squared is the difference between those two. And then you take the square root of each of those. And square root of 12 is 2 squares of 3, but that's approximately 3 point something. So we already have our equation. I'll go ahead and write it again over here. And then from that, what direction is it going? Alright, is it horizontal or is it vertical? Well, because a squared is underneath the y, think y-axis, so therefore this one will be vertical. Center would be at 1, negative 3. Foci once again is C, major is A, minor is B. So 1, negative 3, I'll get the center. Since we are going vertical, we're changing the y value, so we will add C to the y coordinate and subtract it. So negative 3 minus 2 square roots of 3, and then negative 3 plus 2 square roots of 3. But I'm just going to count 3 point something to actually get the distance. 1, 2, 3 something up and down. Now the a value is 4, so you're actually going to add and subtract 4 from negative 3. So negative 3 minus 4 is negative 7. Negative 3 plus 4 is 1. So if I count 1, 2, 3, 4, I'll get at 1, 1. And if I go the other way 4, I will be at 1, negative 7. And then your minor is perpendicular, so you'll be adding to your x coordinate now. And b is 2, so 1 minus 2 is negative 1. And 1 plus 2 is 3. And once again, I'm just going to count 2 to the right and 2 to the left. And those are my those are my minor vertices, negative 1, negative 3, and 3, negative 3. And then you can graph the ellipse from there. And that's it. Alright, and the last example we're going to look at is working backwards. So I've given you a graph because sometimes I think it's easier if you have a graph to graph it to kind of work backwards as to what you need to know. Now remember, for an ellipse equation, you need the center and you need the a and the b value. So on this particular example, I've given you the foci. So at negative 2, 1, and at negative 2, negative 7, we have the foci. Well, what does that give you? Well, it gives you the distance between the two, which means you can find the center. So you're finding the average, or the midpoint between 1 and negative 7. So that'd be negative 6 divided by 2, because you add them and divide by 2. So that'd be at negative 3. So then we know our center is at negative 2, -3. We also now know that it is vertical. The major axis has a length of 10, so the length is 10. That's 2a. So we know a is equal to 5. So 1, 2, 3, 4, 5 would give the major vertices. Now, the important thing is that we have a is 5. We also now know, or should have known before, but c is equal to 4. So we don't know anything about the minor vertice, but knowing that we have the relationship of c squared is equal to a squared minus b squared, we can plug in the information. So this would be 16 is equal to 25 minus b squared, and we can now solve for b squared. So b squared is equal to 9, and that's what we need. We need the b squared. B would be 3, but for our equation, we just need b squared. So we have x minus -2, so that's plus 2 squared, plus y plus 3 squared, and then that's equal to 1. But we need the denominator a squared and b squared. Which one does, which way do they go? Well, since we know it's vertical, we know the larger one, which is 25, because if a is 20, or if a is 5, then a squared is 25, goes underneath the y value, which is y plus 3. And then the b would go underneath the x. So here's your equation of your ellipse given the foci and the major axis length of 10. Alright, and the last thing I'm really just going to talk about is something called eccentricity. It's the ratio of the focal distance to the vertex distance. E is equal to c divided by a. It measures kind of the ovalness, I guess, so to speak, of an ellipse. It has to be between 0 and 1 for an ellipse, and we know that the a value is greater than the c value, but we also know c must be greater than 0. So really what it comes down to is when you start measuring kind of the ovalness and you divide these values, what we find out is the closer this number is to 1, the more oval the ellipse is, kind of more stretched out it is. The closer it is to 0, the more circular an ellipse is. So that's what eccentricity is. We have eccentricity for all the conics. For a circle, it'll be 0. For an ellipse, which is really what we're looking at right now, that distance will be between 0 and 1, or that measure will be between 0 and 1. Parabola, it'll actually be 1, and then a hyperbola, it'll be greater than 1. But that, once again, is just kind of describing, when you go to measure that, how circular it is or how oval it is, depending on what that value is. And that is it for an ellipse. Once again, write your summary down here as to what those important parts are, and we'll discuss more of this in class as well.